Okay, on to our second part of this lesson, so triaxial shear test. Ngayon, i-differentiate natin kung ano yung ginagawa ng triaxial shear test sa direct shear test. So, ang triaxial shear test, ang ginagawa natin kung actual yung lab, meron tayong sineset up na soil sample doon sa triaxial shear equipment natin. Then what it does is yung soil mo is subjected to a rubber container na bukod doon sa force na ina-exert vertically, ang nangyayari doon sa triaxial shear test ay umiikot ngayon yung soil mo. At given of different directions. Ngayon, what's more specific about triaxial shear test ay more uniform yung stress condition niya. Tapos yung behavior ng soil in terms of the deformation is also given justice dito. So, ang types natin ay consolidated drained. So, meron tayong consolidated undrained and unconsolidated undrained. So, yung tatlong types na to, ang ginagawa is yung fastest procedure is yung unconsolidated and undrained. Yung unconsolidated and drained, total stress ang kino-consider niya. So sa total stress, alam natin na yung effect ng water is still present. So next natin, yung unconsolidated and drained, ginagamit lang natin yan kung cohesive yung soil natin. Next natin is yung consolidated drain. Sa consolidated drain, yung kino-consider natin dito ay yung long-term na effect doon sa soil in terms of effective stress. So kung effective stress ang kino-consider natin, ibig sabihin, inaalis natin yung effect ng water doon sa soil. Or dinadrain natin ngayon yung soil doon sa ano niya, sorry. Wait. Mali ako nang nilagay. So, sa consolidated drain, dito pala sa number 1 yun, ang pino-consider natin dito ay effective stress pa rin. So, sa effective stress, ang ginagawa natin, inaalis natin yung effect ng water para malaman natin kung ano ba talaga yung granular behavior ng soil natin in terms of stresses. Ngayon, ang kino-consider natin dito ay negligible yung pore water pressure. So lastly, doon sa consolidated and drained, under consolidated and drained, ang ginagawa natin ay merong effective stress pa rin ang kino-consider, pero ang iniba niya doon sa effective stress is rapid yung test natin dito. Mas mabilis na effect ng shear yung tinitingnan natin. Okay. So, paano ba yung nag-work yung triaxial shear test? So, kung free body diagram ang titingnan natin, meron tayong kino-consider ulit under sampling na minor principal stress and major principal stress. Pero sa triaxial shear test, ang kino-consider lang natin dito ay minor principal stress. So mapapansin nyo lahat ay sigma 3 doon sa paligid. Pero hindi minor principal stress ang tawag dyan. Sa triaxial shear test, tinatawag natin ang sigma 3 as cell confining pressure. Wherein, syempre, kung lahat ng forces niya ay equal, hindi siya mag-generate ng failure. Pero, kung gagawin natin sigma 1, yung nasa upper portion, pwede na tayong magkaroon ngayon ng effect ng failure for normal and shear stress. Pero paano ba ngayon mangyayari yan? Kung lalagyan natin siya ng deviator stress at failure or additional load or additional stress na po pwedeng i-generate doon sa soil sample natin, pwede ngayon mag-generate ng failure yan. Yung cell-confining pressure or yung chamber pressure plus yung deviator stress would result to sigma 1. So, pwede natin sabihin dito na yung sigma 1 can be equal to the minor principal stress or yung chamber pressure plus yung deviator stress. Yun lang yun siya. So, after that, pwede natin ngayong i-consider sa more circle natin. Ngayon, sa triaxial shear test, syempre, since test yan, ibig sabihin maraming tests, maraming samples, and maraming trials ang dapat gawin. So, kung drawing natin yung more circle na dalawa yung effect, so like the procedure lang naman nung una, kailangan lang ulit natin i-drawing yung y-axis, yung x-axis, and then yung series of points. So, kung dalawang test yan, syempre merong minor and major principal stress for excuse me, for test 1, and then minor and major principal stress for test 2. Syempre yung circle niyan, dalawa rin. And then, dalawang centers din, which corresponds to dalawang point of tangency. Kung dalawang center yan, meaning to say, dalawa rin yung makukuha kong radius. Let's say RA and RB. Ngayon, since isang soil sample siya, meaning to say isang rate lang ng cohesion meron tayo. So for all of the tests, isang uniform value for cohesion lang meron tayo. Ngayon, given na may partner din siya na normal and shear, paano natin ngayon kukuhanin? Ang importante lang dito is makuha natin kung ano ba yung angle of internal friction. So paano natin kukuhanin yung angle of internal friction? Given na meron tayong ganitong figure. So kung kukunin natin yon using yung figures, ang kailangan lang natin dyan ay similar triangles. Yan lang siya. So itong similar triangles na to, alam natin na yung resulting angle would always be equal to the angle of internal friction. And then may uniform value for cohesion. Ano pa? Kung titingnan natin, meron kang distance, let's say angle of internal friction. Tapos may distance ka na pwede natin i-denote as the value of x. Ngayon, kung ganito yung case natin, pwede nating sabihin na meron tayong sigma 1 na equal to sigma 3 plus the deviator stress. Ngayon, ano yung pwede nating malaman about doon sa radius? Mapapansin niyo ulit na yung radius ay equal to, from last derivation natin, ang radius is equal to sigma 1 minus sigma 3, diba? Sigma 1 minus sigma 3 all over 2. Kung titingnan natin dito, pwede natin sabihin na yung deviator stress can also be equal to sigma 1 minus sigma 3. Therefore, yung radius natin is equal to the deviator stress all over 2. Yan lang ngayon yung value ng radius natin. So regardless kung RA or RB, ang radius ay deviator stress all over 2. Ngayon, we can also say na yung center, C1 and then center 2. Yan. Pwede natin sabihin na yung center can be also equal to yung sigma prime 3 So, center is equal to sigma prime 3 plus yung radius ng natin. Therefore, pwede mo ulit sabihin dyan na yung center can also be equal to sigma prime 3 plus the deviator stress all over 2. Ngayon, kung titingnan natin itong malaking triangle na to, ang pwede nating consider now is meron tayong dalawang right triangles na equally associated. So, equally associated siya, mapapansin nyo, ang center ngayon, yung magiging hypotenuse niya. So, kung may dalawang triangles dyan, mapapansin nyo, yan, meron tayong radius at A, and then center 1, ito yung X, diba? And then yung second triangle, meron din value ng X dito, pero nasa center 2 na, and then meron tayong radius at B. So with this, anong trigonometric function ang dapat natin gamitin kung alam natin na angle of internal friction itong resulting, and then given yung radius? Alam natin na po pwede natin gamitin yung sine function. So, to acquire yung sine phi prime, ano yung dapat natin gawin between radius and center? Then natin sabihin na sine phi prime is equal to, sine is equal to the opposite over hypotenuse, di ba? So, ibig sabihin yung sine can be equal to the radius all over the x plus center. Hindi natin alam yung value ng x. So, try natin gawin. Pwede natin sabihin na this is radius b minus radius a. Since dalawa yung sample natin, minus x plus center ng a minus x plus center, x plus center pala ng b minus x plus center ng a. Ano yung mapapansin ngayon? Kung mapapansin nyo, yung x na value ay parehas lang. Since same point of origin lang naman yung vertex ng angle phi prime natin for both triangles A and triangle B. So, yung x natin can be cancelled na. Therefore, pwede nating sabihin ngayon na sine phi prime is equal to RB minus RA all over the center of B minus center A. Therefore, para makuha yung phi prime, meron tayong dapat na function, na inverse sine ng radius all over center. So, upon determining yung phi prime, pwede mo na ma-determine dyan yung shear stress at failure, yung normal stress, and yung value ng cohesion. So, sa triaxial shear test, ang hinahanap natin kadalasan ay itong mga components na to. Okay? So, gagamitin lang natin yung principle earlier. Okay, so proceed tayo. Next problem. So, sa problem 2 natin, meron tayong 7 meter thick soil layer has a water table of 3 meters below the ground surface. The soil above the water table has a degree of saturation of 45 degrees, void ratio 0.4, and specific gravity of 2.7. So tests show that the soil have an angle of friction of 32 degrees and cohesion of 14.6 kilopascals. What is the potential shear strength of soil on horizontal plane at a depth of 2 meters below the ground surface? Okay. So sa situation natin, meron tayong 7 meters down na soil layer. So do sa 7 meters sa soil layer na yan, merong water table of 3 meters below ground surface. Ngayon, doon sa water table, so kung 3 meters yan, so yung soil natin na hindi below the surface of water is 4 meters. So the total is 7 meters. Ngayon, ang soil above the water daw has a degree of saturation na equal to 45%, void ratio na equal to 0.4, specific gravity of equal to 2.7. Ang hinahanap natin ay meron daw angle of internal friction na phi prime na equal to 32 degrees and cohesion na equal to 14.6. Effective ang ginagamit natin or yung total stress since wala naman siya sa tubig. Ngayon, ang hahanapan daw natin ng shear stress ay yung depth 2 meters below. So, paano natin siya hahanapin? Ngayon, before natin hanapin yan, ang alam natin sa stresses in a soil mass, kung meron tayong point of reference, meron tayong makukuhang corresponding na total or normal stress. So, at point A, para malaban natin yung normal stress or yung effective stress since dry naman yung soil or moist yung soil. And wala tayo doon sa water level, so hindi natin kailangan yung neutral stress or yung per water pressure. Ang kailangan lang natin malaman is yung normal or yung effective stress. So yung normal is equal to effective since wala namang intrusion ng water. Pwede natin sabihin na iyan ay equal to gamma times h. Ang height natin ay 2 meters. So para malaman natin yung information with regards to the unit weight, paano natin kukuhanin? Yung unit weight na gagamitin natin na moist is equal to, natin sabihin na equal to specific gravity plus SE times unit weight of water all over 1 plus E. Diba? So, in this formula, pwede natin sabihin na meron tayo specific gravity na 2.7 plus yung effect ng degree of saturation na 0.45 times 0.4 times unit weight of water na 9.81 all over 1 plus E. So 1 plus 0.4. Yung unit weight na moist now is equal to ilan? So meron tayo 2.7 times 0.45 ay plus yung quantity 0.45 times 0.04 0.4 rather times 9.81 all over 1 plus 0.4. Moist unit weight now would be equal to around 20.18 kilonewton per cubic meter. So 20.18 kilonewton per cubic meter. Now, after determining yung moist unit weight, yung normal stress naman natin ang dapat natin hanapin. So yung normal stress at point A. So pwede natin sabihin na yung normal stress at point A is equal to gamma H lang. So meron tayo 20.18 multiplied by 2. Normal stress now is equal to 40.36. Ngayon, since wala naman siya sa water level and di naman natin kailangan bawasan yung effect ng water, pwede na nating tingnan ngayon kung ano pa ba yung dapat gawin. So in this problem, ang dapat natin gawin next is to draw a Morse circle. So to draw yung Morse circle natin, let's say, mas okay pala na doon na lang sa isang screen. So, balik tayo dito sa screen na to. So, para i-drawing yung Morse circle now, kailangan muna natin malaman ulit kung ano ba yung mga information na meron. So, may angle of friction tayo na 32 degrees and cohesion na 14.6. Meaning to say, kapag nag-draw tayo ng Morse circle, this point, alam natin na for x and y axis, medyo extended yung x-axis natin. And then, since meron tayong cohesion, alam natin na may height na yan. So, ang cohesion natin is 14.6 and the angle of internal friction of V prime is equal to 32 degrees. So, from here, pwede nating i-consider may Morse circle uli. Pero taka lang. Liitan natin yung bilog para medyo attainable yung drawing. Yeah. So, meron tayong 14.6 and then meron tayong angle of internal friction na 32 degrees. So, yung Morse circle natin, so from minor principal stress papunta doon sa major principal stress, say, yan na yan. Tapos, mula doon sa point of tangency, pupunta doon sa radius. Yan tayo niya. So, alam natin na meron tayong normal stress at point A na equal to 40.36. Saan ngayon yung location ng normal stress? Sa minor principal stress, sa major principal stress, or dito sa point of tangency. So, alam natin na for every normal stress, may combination ng shear stress na nagkakos ng failure. So meaning to say, meron tayong shear stress at failure and yung normal stress at point A ay nakatapat ngayon dito. Ang normal stress at point A ay 40.36. Yan ngayon yung 40.36. Nandito sa point na to. So hindi siya major principal stress, hindi siya minor principal stress. Andun siya sa may mismong normal stress. Now, ang hanapin daw natin ay potential shear strength. Ibig sabihin, yung buong shear stress at failure yung dapat nating hanapin. Paano natin hahanapin yung shear stress at failure? Pwede nating hanapin ngayon using yung figure na to. So, let's say meron tayong H. And then, syempre, yung 14.6, mag-extend na lang din doon sa baba. Since parehas lang naman ang height yan. Pwede natin ulit sabihin na yung shear stress at failure can be equal to the cohesion plus yung value ng H. Yung H natin, paano natin kukuhanin? Yung H is a function of yung 40.36 na normal stress and yung angle of internal friction natin na 32 degrees. Pwede natin sabihin na yung H is just equal to 40.36 or yung normal stress multiplied by tangent phi prime or 40.36 tangent 32 degrees. So yung shear stress natin at failure is equal to 14.6 plus 40.36 tangent 32 degrees. Shear stress at failure is now equal to So meron tayong shear stress at failure na 39.82 kilopascal. So yan ngayon yung required or yung potential shear strength capacity ng soil natin for problem number 2. Okay, so next problem number 3. So meron tayong normally consolidated clay na merong results ng drain triaxial shear test with a chamber pressure of 112 kilopascal and deviator stress at 175. Now, first agenda natin is to determine the angle of internal friction, prime, the angle of the failure plane makes with the major principals plane, meaning to say yung theta, and yung normal and shear stress at failure. So, yung sigma prime saka yung shear stress at failure. So, given itong information natin, kung normally consolidated clay, ang normally consolidated clay is cohesionless. So kapag normally consolidated yung clay natin, ina-assume natin yan na cohesionless. Therefore, yung C prime natin is equal to 0. Kung C prime is equal to 0, pwede nating i-plot yung Mars circle natin, position wherein nasa origin ngayon yung vertex natin. Time kung gagawa ko ulit ng Mars circle. And then, so basic principle, kailangan nating i-plot ngayon yung chamber pressure and yung deviator stress. Yung chamber pressure is yung cell-confining pressure na tinatawag natin or yung sigma 3. Yung deviator stress, alam natin na yan ay yung delta sigma D. Ngayon, sa Mohr circle natin, ang chamber pressure is yung first point. Tapos, syempre, ito yung center. And lastly, ito ngayon yung sigma 1. Importante ba na kung makuha natin yung sigma 1? At this point, hindi. Ang kailangan lang muna nating malaman is ano ba yung value ng center. So wala pa tayong angle of internal friction. Ang hahanapin daw natin ay yung angle ng failure plane, meaning to say, this one. So 2 theta. And then, pwede na natin hanapin yung center. So yung center is just equal to sigma prime 3 plus, yung na-derive natin earlier na plus delta sigma d all over 2. So meron tayo 112 plus 175 over 2. Center now is equal to, ang center ay 199.5 kilopascal. Now, bukod doon sa center, pwede na rin natin ma-derive yung value for radius. Yung radius kasi natin, radius now is just equal to the deviator stress over 2. Since alam natin na iyan ay also equal to the radius. So meron tayo 175 all over 2. Radius is equal to 87.5 natin. All in kilopascal. Now, kung titingnan natin, paano ba natin makukuha ngayon yung angle of internal friction given na may radius tayo? Daan natin nung last derivation, kung may cohesion, pwede nating i-manipulate yung triangle into 3 different figures. Ngayon, kung cohesionless siya, we can only refer to 2 different figures. Kung ipa-plot natin yun nandito sa point of tangency na may combination ng normal and shear stress at failure, pwede natin i-project yung line below. Pag pinroject natin yung line below, meron tayong mare-reflect ulit na angle of internal friction. So this is figure 1 and figure 2. Referring to figure 2, so, meron tayong figure 2. Ang figure 2 natin ngayon, pwede natin makuha yung angle of internal friction dyan. Pwede natin gawan ng relationship yung value ng R. Diba? Yung R kasi, kung makikita, kung mapapansin natin, right triangle yan. Yung R ngayon, yung magsiserve as, yung R ay magsiserve as the hypotenuse of the triangle. Pero, kung titingnan natin yung case na to, hindi pa dito po pwede. Bakit? Wala pa tayong angle of internal friction. So, ano lang muna ba yung pwede natin gawing basehan? Yung pwede natin gawing basehan is yung buong triangle. Yung combination of both figure 1 and 2. So kung both figure 1 and 2 ang titingnan natin dyan, so ihiwalay natin. Meron tayong radius R, meron tayong center, and meron tayong angle of internal friction na equal to P prime. Yung center natin dito, alam natin na yung center ay equal to 199.5. Meaning to say, from the origin hanggang center, ang distance niyan would be equal to 199.5. Ngayon, ano yung pwedeng entail nito? Alam natin na right angle yung nasa point of tangency. between the radius and the failure envelope. Ngayon, 199.5 yung center, meaning to say 199.5 yung hypotenuse ng triangle natin, na right triangle. Therefore, to find phi prime, ano yung gagamitin natin? Pwede natin sabihin na sin phi prime is equal to the opposite over hypotenuse, or yung radius divided by 199.5, wherein yung radius natin, this point is equal to 87.5. So 87.5 all over 199.5. Therefore, yung phi prime natin is just equal to the inverse sine of 87.5 all over 199.5, wherein phi prime now is equal to ilan? Phi prime now at this point ay equal to 26.014 degrees. So, nakuha na natin yung unang answer. Next, after acquiring yung value of phi prime, ang next natin is yung value ng theta. So, for the value of theta, po pwede natin gawin dyan is yung may standard formula for that. So, yung 2 theta, kung mapapansin nyo, ang resulting yan is 180 degrees. So, titingnan natin yung figure. Meron tayong 2 theta. And then, kung referring to figure 2, meron tayong phi prime na equal to 26.014. Ngayon, since right triangle yan, pwede mo lang sabihin na ito, let's say this is alpha. Pwede natin sabihin na alpha is equal to 180 degrees minus 90 degrees minus 26.014 degrees. Alpha now is equal to that. Alpha is equal to 180 minus 90 minus 26.014. Alpha is equal to 63.986. Ito ay figure 2. So, next natin, referring doon sa right angle natin, balik tayo. So, meron tayong 2 theta and meron tayong 63.986. So, doon sa 63.986, pwede natin sabihin na yung 180 is equal to 2 theta plus 63.986. Yung theta ngayon ay pwede natin sabihin na equal to 180 plus 63 minus 180 minus 63.986 all over 2. Theta is equal to minus 63.986 divided by 2. Meron tayong 58.007 degrees. Yan ngayon yung angle theta. Mayroong shortcut dyan. Pwede natin gawin na yung theta is equal to 45 plus phi prime all over 2. Pwede rin yan na magre-result dito sa same angle of internal friction. So, next natin is yung since meron na tayo nakuhang angle of internal friction, pwede na natin makuha yung shear stress at failure. So, figure 2, sa figure 2, pwede na natin makuha yung shear stress at failure, wherein shear stress at failure is just equal to R cosine phi prime. So, R cosine phi prime, meron tayo 87.5 cosine 26.014. Shear stress at failure is now equal to 78.635 degrees. Ay, sorry, not degrees, but kilopascal. So, lastly, yung normal stress. So, yung normal stress, natin ay nandito na. So, to get the normal stress, ano yung dapat mong gawin ngayon? Normal stress is just equal to the center minus R sine phi prime. So, yung center, since 199.5 minus R sine phi prime, or yung tinatawag natin na base B. So, yan na natin ulit. I-re-equate natin. So, effective stress, or yung normal stress, is equal to center minus B. Ito yung B, nagaling doon sa, then ito ay normal stress. Or pwede natin sabihin na center minus R sine phi prime. So, R minus sine phi prime, pwede natin i-compute ngayon yan. Pwede natin sabihin na yung center ulit natin ay equal to 199.5 minus 87.5 sine 26.014. Normal stress is equal to 160.6 Newton. Kilopascal. And ngayon, yung final answers for problem 3. Okay. So, yung questions natin uli, i-send sa akin through Messenger or pwede doon sa Google Classroom. Next. So, second to the last problem, problem 4. Meron tayong dalawang triaxial shear test na kinonduct for this specific problem. So, this is test 1 and test 2. Ang kailangan nating determine is effective angle of internal friction and yung shear normal stress and cohesion in drain condition at sample 1. Meaning to say, kapag nakuha na natin yung phi prime, ang kailangan na lang natin malaman ay yung normal stress saka yung shear stress at failure dito sa first sample. So, paano ba natin gagawin yan? So, una munang gagawin is alam natin dito sa problem, ang hinahanap ay effective. So kung effective angle of internal friction ang hinahanap, ang effective natin, alam natin dapat ay may normal na effective stress ang gagamitin natin. Where yung effective stress is just equal to the total stress minus neutral stress. Or yung pore water pressure. So, under pore water pressure, pwede nating i-state now that this effective stress can be determined. So from cell pressure, yung cell pressure natin can be denoted as the normal stress. Diba? Or yung total stress natin. Meaning to say, yung effective stress makukuha na natin agad yan. So, at test 1 and test 2. Test 1, ang effective stress natin is equal to 200 minus 142.5. 200 minus 142.5 is equal to 57.5. Sa next natin, ang effective stress, so sa test 2, meron tayong 400 minus 275.5. 400 minus 275.5 is equal to 124.5. Kilopascal. So, ano lang yan, kumbaga parang wordplay. Makikita mo dyan na kailangan mong alisin yung water o yung effect ng neutral stress if effective angle or if may effective shear or effective normal ang ipapakita. Pero kung wala naman, and then given pa rin yung neutral stress, trick question na lang siya. Okay? So, sariling judgment. If walang effective, hindi natin kailangan alisin yung neutral stress. Not unless sabihin na consolidated drained or consolidated undrained yung test na gagawin. Okay. So, given na may information na tayo with regards to the effective stress, so, i-retain natin yung value ng effective stress para hindi makalimutan. Ang next natin is ipa-plot natin yung Mohr circle. So, kung ipa-plot natin yung Mohr circle, draw mo ulit, na y-axis and then x-axis. And then from that, yung failure envelope. Tapos, yung series of points. So, sa atin, ang normal stress natin na nandito is yung cell pressure. So, i-denote natin as different colors na lang. So, dito sa point 1 natin, pwede natin sabihin na this is 57.5. And then, kung magpo-form na tayo ng Mohr circle, yung katandem niya is this one. Tapos, yung para sa doon sa second stress, meron tayong value na equal to 124.5. Tapos, yung katandem ulit niya is this one. Ngayon, dito sa mga series of points natin, kailangan nating malaman kung ano ba yung center. So, doon sa center natin, parang kung mapapansin nyo, hindi na significant na hanapin yung nandito sa gilid, yung major principal stress. Pero for brevity or for educational purposes, kailangan natin siya pakita. Okay, so this is center 1. Tapos yung center 2 natin is this one. So this is sigma 1. Ganun na lang natin. Leave it blank na lang muna. So kung i-form natin yung Mohr circle, so para doon sa test 2, And then yung isa ay para sa test 1. Ngayon, yung point of tangency for point 1, pwede natin i-reflect doon sa center. Kaya magkakaroon na tayo ng first radius. Next, point of tangency ulit for second test, mula doon sa failure envelope, papunta doon sa center, meron na tayong second radius. Ngayon, itong given na to, alam natin na yung radius pwede natin makuha doon sa deviator stress. Diba? So, sa radius, doon natin makuha yung R1. R1 is yung deviator stress na 1 all over 2. Wherein yung deviator stress natin earlier is at 119. Radius 1 is equal to 59.5 kilopascal. Next naman yung second radius. Radius 2 is equal to deviator stress pa rin na second all over 2 or equal to 143.2 or 143 rather divided by 2. Second radius is equal to 71.5 kilopascal. Ngayon, after determining yung radius, pwede na natin makuha ngayon yung center. So for center, meron tayong dalawang centers ulit. So meron tayong CE1 na equal to yung effective stress o yung cell pressure plus iyan na natin yung base equation para masaya. So center is equal to the chamber pressure plus yung corresponding radius. So center 1 is equal to sigma prime 3 na equal to 57.5 plus yung radius natin na 59.5. Therefore, yung center natin is equal to ilan ngayon? 117 kilopascal. So, 117 yan. So, sa second center natin, meron tayong 71.5 na radius. And then, yung minor principal stress natin or yung cell confining pressure na 124.5. Ang second center natin ay equal to 196 kilopascal. Ngayon, after solving for the radius and center, pwede na natin makuha ngayon yung angle of internal friction. O paano natin kukuhanin yung angle of internal friction on this one? Paano natin kukuhanin yung angle of internal friction? Yung angle of internal friction uli ay nandito sa vertex natin wherein na-derive natin earlier kung ano yung equation na dapat natin gamitin, di ba? Using yung dalawang triangles na present. So, i-project na lang uli natin yung dalawang triangles. So, sa portion na to, may x daw uli na nag-exceed. Pero given doon sa formula, hindi na natin siya po pwede, or hindi naman natin siya talaga dapat gamitin. So therefore, meron tayong inverse sign ng ng radius over center, di ba? So radius 2 minus radius 1 all over center 2 minus center 1. So inverse sign Phi prime is equal to inverse sine ng R2, 71.5 minus 59.5 all over center na 196 minus 117. Phi prime now is equal to ilan? Meron tayong 8.737 degrees. Yan ngayon yung angle of internal friction or yung answer doon sa first question. Now, next question natin is, ano raw yung shear stress, normal stress, and cohesion in drain condition at sample 1. So kung sample 1 ang titignan natin, magre-refer lang tayo doon sa elements na meron yung first center or yung first Morse circle natin. So doon sa first Morse circle natin, yung cohesion naman kasi is uniform all over the specimen. So kahit yung sample 2 ang kuhanin. Pero syempre, yung normal and shear stress would remain at sample 1 kasi magkaiba ng rate niya. Tapos, yung mga Morse circle elements natin would remain the same for sample 1. Okay, so solving for the second portion ng problem solving natin, kailangan natin i-plot ulit yung mga elements natin. So for sample 1 or test 1, meron tayong radius na equal to 87. May radius tayo na equal to 59.5. And then meron tayong value ng center na 117. So yung 117 is mula dito sa origin. So meron tayong value na equal to 117. Tapos dito, ipaproject ulit natin yung mga figures na na-derive natin from earlier. So, triangle, and then another triangle and rectangle. So, meron tayong figures 1, 2, and 3. Ngayon, from here, meron tayong makukuha na values for normal stress and shear stress at failure. So this one is the shear stress at failure and this one is normal stress. Ngayon, importante pa ba na gamitin natin yung self-confining pressure? Sa point na to hindi nag-aano. So dito tayo pwede mag-lean para for shortcut purposes, ganun ba? Okay. Angle of internal friction is equal to 8.737 degrees. So uniform yan. This is also equal to phi prime. And yung projected angle mula doon sa point of tangency is also equal to phi prime. Ngayon, pwede agad natin makuha yung shear stress at failure. Paano? Yung shear stress at failure can be denoted as this side. So refer to figure 1. Yung shear stress at failure natin can just be equal to R cosine phi prime. Kasi right triangle yan. And then yung radius can also be equal to the hypotenuse. Pwede natin sabihin na this is equal to 59.5 cosine phi prime na 8.737. Shear stress at failure is now equal to 58.81. Kilopascal. Yan ngayon yung shear stress at failure. Next natin, so kung titingnan natin yung next figure, which is figure 3, figure 3 and figure 1. Sa figure 3 and figure 1, ang kailangan daw nating hanapin ay yung normal stress. Yung normal stress ay mula dito sa point of origin hanggang dito sa distance na to. So, kung hanapin natin yan, pwede natin sabihin na, let's say, figures 1 and 3. Sa figure 1 and 3, kung mapapansin nyo, yung ano natin, yung triangle natin pero base na B. And then, yung center pa rin natin na point. Ngayon, kung titignan natin, pwede natin sabihin na yung normal stress, or let's say yung center mismo, center is equal to the normal stress plus B. So, pwede nating sabihin dyan na yung normal stress is equal to the center minus yung value ng B. Wherein B can be derived as the opposite side, di ba? So, we need to say B is equal to R sine phi prime. So, yung normal stress natin is equal to the center which is equal to 117 minus R sine phi prime or 59.5 sine 8.737 degrees. So, your normal stress now is equal to 107.962 kilopascal. Lastly, yung cohesion. Yung cohesion, kung titingnan natin, ang pwedeng rate niyan is in terms of shear stress. Kasi yung cohesion, pwede nating makuha yung side na cohesion and also this side. So, yung cohesion, pwede natin makuha as a result of figures 2 and figure 3. Since dun sa figure 2, pwede natin sabihin na meron tayong height nung figure 2. So, for figure 2 and 3, pwede natin sabihin na yung shear stress at failure can be equal to the cohesion plus yung height ng triangle at figure 2. So, yung height ng triangle at figure 2, pwede natin makuha agad yan. Since meron na tayong known value para doon sa normal stress, which is equal to 107.962. Pwede mo rin i-extend ngayon yung 107.962 doon sa taas. Okay. So, given na yung triangle natin ay meron ng mga properties, pwede na natin masolve ngayon kung ano ba yung value ng cohesion. Pwede natin sabihin na yung cohesion is just equal to the shear stress at failure minus yung height ng triangle. So, natin sabihin na cohesion is equal to the shear stress, which is 58.81, minus yung height ng triangle, which is equal to 107.962 tangent phi prime. Cohesion is now equal to 42.22 kilopascal. Yeah. So, yung problem 4 natin is that. So, yung cohesion i-emphasize ko lang ulit na yung height ng triangle dito is equal to normal stress tangent phi prime. Okay? So, last problem. Sa last problem natin, meron tayong cohesionless soil sample na may critical state friction angle na 28 degrees and a normal effective stress at failure of 200 kilopascals. So, pag drawing natin yung mark circle ulit, mali yata ito. Teka lang. Mali yung figure. So, wag natin pansinin itong figure. Tatakpak ko na lang. Takpan natin. Yan. So, yung figure natin, since ang ano daw natin, ang Mohr circle daw natin ay ang soil sample natin rather ay cohesionless. Ang gagawin natin is i-plot muna natin yung Mohr circle. So kung cohesionless yung circle natin, sa point of origin agad, mapupunta. So, gawa tayo ng Mohr circle. And then, need natin i-plot ngayon yung mga elements nila. So, sa elements nila, ang given lang natin ay yung angle of internal friction na equal to 28 degrees and yung normal stress at failure of 200 kilopascal. Meaning to say, itong 200 kilopascal ay yung equivalent normal stress na agad. So what we need to find are, first, yung shear stress, so syempre, combination ng normal and shear stress, yan. So this is normal shear stress at failure. Ang next nating hanapin daw ay yung deviator stress. Ang deviator stress na kailangan nating hanapin ay yung buong diameter ng Mohr circle. And lastly, yung cell confining pressure. So, ang hahanapin din natin is this one, yung sigma 3 prime. Okay. So, paano natin gagawin? So, sa critical state shear stress, medyo madali na lang yan. At some point, paano natin ngayon makukuha yung shear stress at failure given yung normal stress? So, kung given yung normal stress, ano yung pwedeng mapansin? Pwede rin nating i-take note na itong angle na ma-form dito is also equal to the angle of internal friction. Pero dito ba tayo agad magre-resort? Hindi pa natin alam kung ano yung radius. So therefore, hindi pa natin siya po pwedeng galawin. Ano lang yung po pwede natin gamitin at this point? Ang pwede natin gamitin at this point is this figure na right triangle din. Meron tayong angle of internal friction na 28 degrees and normal stress na 200 kilopascal. Therefore, pwede nating makuha ngayon yung height ng triangle or yung shear stress at failure. Wherein, shear stress at failure can be equal to yung normal stress tangent 28 degrees or normal stress tangent phi prime. So, pwede natin sabihin na this is 200 tangent of 28 degrees. Shear stress at failure is now equal to 106.34 kilopascal. Next, after determining yung shear stress, ang dapat natin makuha ngayon ay yung deviator stress at failure. So, referring to the triangle earlier na isa, meron na tayong shear stress na 106.34. Ang radius is this one, and may angle of internal friction tayo na 28 degrees. So, assuming this, pwede na natin sabihin na, iibahin natin ang kulay. Pwede natin consider ngayon na yung radius is equal to, ano lang yun? Yung radius is yung hypotenuse. Pwede natin sabihin na yung shear stress ng failure can also be equal to R cosine 28 degrees. Pwede natin consider na 106.34 is equal to R cosine 28 degrees. So therefore, yung radius natin is equal to 120.44 kilopascal. Pero hindi pa tayo tapos dahil radius pa lang yan. Alam natin na yung deviator stress is equal to twice ng radius. So therefore, yung deviator stress at failure natin is now equal to 240.88 kilopascal. So yan na ngayon yung deviator stress. Ang last natin for this problem is to find yung a major principal stress. Sorry, not the major principal stress, but the minor principal stress or yung cell-confining pressure. So para makuha yung cell pressure, ang pwede natin gawin dyan is, kunin natin yung center and then i-less natin doon sa radius. So yung cell-confining pressure is equal to the center minus yung radius. So the center now, makukuha natin siya using yung normal stress. Yung normal stress plus yung side na to earlier na let's say yung base yan ng triangle natin at figure 2. So plus B. Natin sabihin na this is 200 plus. Paano natin kukuhanin yung B? Kung R cosine yung kanina na shear stress, this would be the sine side. So R sine 120.44 sine 28 degrees. Yung center natin is equal to 256.543 kilopascal. So, yung cell-confining pressure natin ngayon is equal to 256.543 minus 120.44. Cell-confining pressure is now equal to 136.1 kilopascal. So, yan ngayon yung resulting stress natin. So, yung mga questions ulit natin ay i-entertain ko for the whole week para sa mga questions or anything you need to clarify. Okay? So, yung announcements muna tayo. So, sa mga announcements natin, yung problem set 2 ang deadline ay bibigay ko. Pero, i-upload ko rin siya sa Google Drive. At the same time, yung deadline ay 1 week prior sa given date, which is 1 week from today. At the same time, yung quiz 2, same lang din ang deadline date ng problem set, pero yung pag-upload ay magka-comments doon sa same day. Tapos yung midterm exam is a week after the second quiz. Pero ano natin to, i-revise natin kasi we don't have much time. So ang deadline ng ano natin ng problem set 2 ay on Friday, November 13. Tapos yung quiz 2 din ay Friday, November 13. Tapos yung midterm exam natin ay November 20. Yan, siguro fair enough na preparation na rin yan. Okay? So, kung any questions uli, maki-refer na lang doon sa natin, doon sa Gmail natin or sa classroom natin. Okay? So, thank you.